Welcome to Math260, Lesson 1, Introduction to Vectors. Well, what is a vector? The one way to think of a vector is a directed distance. And a way to illustrate this is, suppose somebody says there's a great party at Bob's house, and you say, well, how do I get there? And they say, oh, it's easy, you just go 23.6 miles. Well, what question comes up? Of course, but what direction? And suppose they say, well, there's a party in Minneapolis. It's easy to get to. You just go northwest. Well, the question is how far, right? So if all I have is a direction, I don't know which way to go. No, don't know how far to go. And if all I have is a distance, I know how far to go, but I don't know in which direction. When I have both together, a directed distance, then I know exactly how far to go and in which direction. And this is the geometric idea of a vector. Scaling a vector means multiplying by some non-zero constant. All it does is change the length without changing the direction. So if this vector is scaled by 1 now, if I scale it by more and more and more, the scaled version grows. There's 3 times that vector. Same direction, but 3 times longer. If I scale by a negative amount, then the vector goes in the exact opposite direction. So multiplying by -2 means exactly the opposite direction of what the original vector was and twice as long. So that's the idea of scaling a vector. All it does is change the length, but not the direction, unless it reverses it, of course. Vectors can also be added together in a geometric way. We can define the sum of two vectors by placing the tail, the starting point of the second vector, at the end point or head of the first vector. So here I've constructed the vector w as the vector u plus the vector v. And notice to add u and v, I start at some origin point. I go along u for some distance, its length, and then I start v not at the origin, but at the end of u. So u plus v is this way. And of course, if I change the lengths of these vectors or their orientations, the idea still applies. The vector sum is called head-to-tail addition because I place the tail of the second vector on the head of the first, and the sum is this vector w, which goes directly from the origin to the end of the second vector. Now we can also represent vectors using coordinates. In two-dimensional space we need an x and y component. In three-dimensional space we need an x, a y, and a z component. Now notice that we called these ordered pairs or ordered triplets. That's because the vector AB is not the same as the vector BA in general. Here's a vector with coordinates 2, 3. It means go over 2 in the x direction and up 3 in the y direction. And that's a completely different vector than the vector 3, 2, which goes over 3 in x and up 2 in y. So that's why they were called ordered pairs, because 3, 2, for example, is not the same as 2, 3. Now if I want to go into the second quadrant, I have to make my my x value negative. I can do that by sweeping across this way. This vector has elements minus 3.4 and 2 because I go over negative 3.4 or 3.4 units in the negative x direction and then up 2 in y. And I can also drop into the third quadrant where both of the values, both the x coordinate and the y coordinate, are negative, and then of course back into the fourth quadrant where the x value is positive and the y value is negative. In general, we can represent a vector in n-dimensional space as an ordered n-tuple of the form x1, x2 up to xn, where each of these are real numbers representing the first coordinate, the second coordinate, the third coordinate, etc. So for some examples, this vector u is defined as with coordinates -8, 2, and 7 is an element of three-dimensional space. That's what the R3 stands for. 3 dimensions where each of the elements is a real number. So this would be -8 in the x direction, 2 in the y direction, and 7 in the z direction. This vector v is an element of R5, that is 5-dimensional non-physical space, where the first element is 1, the second element is 2, etc. 5 coordinates makes v a vector in 5-dimensional space, or we call it R5. And here's an element in 2-dimensional space where the coordinates happen to be fractions, rational numbers. Another common way to represent vectors is in column form, essentially as an n by 1 matrix. So for example, the vector u written this way as a column vector is the same vector with elements 8, 2, and 7. That's an element of R3, or 3-dimensional space. V is written as a column vector as an element of 5-dimensional space, and this vector w, notice the elements aren't integers, they're not fractions. The square root of 2 and pi are both irrational, but that's still real numbers. Square root of 2 is a real number, pi is a real number. This is a vector in 2-dimensional space, R2. Now we can also add vectors algebraically. The way we add them algebraically is to add element by element. That is the vector u with elements x1, x2 up to xn, and the vector v with elements y1, y2 up to yn. I add them by adding the corresponding elements. x1 plus y1. The next element is x2 plus y2. The third element is x3 plus y3, etc. So for some numerical examples, if I add the vector -6, 2, 8 to the vector 4, 3, -1, I simply add the corresponding elements. -6 plus 4 is -2. 2 plus 3 is 5. 8 plus -1 is 7. And if I add these two vectors, 2/3 plus 7/8, if you do the arithmetic with a little care, you'll see that that's 37/24, and 3/5 plus 3/4 is 63/5 when you do the arithmetic, the fraction arithmetic, carefully. We can scale a vector algebraically simply by multiplying each element, each coordinate in the vector by the scale factor. So if I multiply s times the vector with coordinates x1, x2 up to xn, the resulting vector is s times x1 for the first element, s times x2 for the second element, etc. So here's an example. We multiply 5/3 by the vector 3/7, 4/5, 11/3. Well, 5/3 times 3/7 is 5/7. 5/3 by times 4/5 is 4/3. Nice cancellation there. And finally, 5/3 times 11/3 is 55/9. And so that's the resulting vector. We'll be able to show, and we will later, that geometric vector addition and algebraic addition really are the same things. And the same thing is true with geometric scaling and regular length scaling. But what we need to know about the length of a vector and angles between vectors to do this, so we'll leave that to a future lesson. So here for some practice. Given these three vectors in three-dimensional space, we could say that these are elements of three-dimensional space. Do the following computations. Compute -2 times the vector v, compute the vector sum u plus v, compute the vector v minus w, which is really v plus -1 times w, and then this linear combination of vectors. So please pause the video now and work these exercises before we reveal the solutions. Okay, hopefully you worked those exercises. Let's see how you did. -2 times the vector v has elements -2 times 2, minus 2 times 1, and minus 2 times 6. Minus 2 times 2 is minus 4, minus 2 times 1 is minus 2, and minus 2 times 6 is minus 12. So this is the resulting vector for negative 2v. To add the vectors u and v, we add the corresponding elements. 3 plus 2 is the first element, 5 plus 1 is the second element, negative 4 plus 6 is the third element. The arithmetic shows the first element is 5, the second element is 6, and the last element is 2. So that's the vector, which is the sum of u plus v. V minus w is, we take the vector v and we subtract the corresponding elements. Or the other way to think about it, we take this vector w and multiply it by negative 1 and then add it. So 2 minus minus 3 is 2 plus 3 is 5. 1 minus 4 is negative 3. And 6 minus 9 is minus 3. So that's the vector difference v minus w. And then the linear combination, the last one, 2u plus 4v plus 3w, I multiply through by 2, and column vector notation is handy here. If I multiply this through by 2, I get 6, 10, negative 8. If I multiply the 4 by v, I get 8, 4, and 24. And if I multiply negative 3 times w, I get 9, minus 12, 27. And then when I add those corresponding vectors, 6 plus 8 plus 9 is 23. 10 plus 4 minus 12 is 2. And negative 8 plus 24 minus 27 is minus 11. So hopefully you got those answers. So for homework, please study Lesson 1 that's posted to D2L on the online notes. This material is also covered in our textbook in section 1.3 if you chose to have a textbook. In our next class on Friday, we'll work lots of exercises involving geometric and algebraic vector addition. And if you want to look ahead, I'll let you know when the video for lesson 2 is posted, the vector dot product. That ends our lesson.